Hey everybody, in this video I'm going to walk you through the answers to this question that is about ethanol being heated and decomposing to produce two gases, C2H4 and water vapor. This has been adapted from an older AP chemistry exam FRQ, so if this diagram or even these numbers look familiar, that might be why. And the actual questions we're answering are down here, A, B, and C, which should be slightly different from that original. Regardless, let's get into it. The first thing you're going to want to do with any AP Chemistry FRQ is sort of cut through the mountain of information you're being presented with just by reading everything. And as you read, you want to underline, circle, or otherwise indicate stuff that looks like it might be important. So I'm going to do that now, starting here. Some glass wool is soaked in ethanol and heated in the presence of a solid catalyst. The ethanol decomposes, producing ethene gas. The diagram below shows the apparatus used to conduct this experiment, collecting the ethene gas as it bubbles into an inverted test tube. Prior to the start of the reaction, the test tube was completely full of water. So mostly what this paragraph is doing is just describing to me what the reaction is that's taking place, which they show down here as well, so that's not super helpful. I do get the names for these things, like now I know that C2H4 is ethene. I know that C2H5OH is ethanol. Obviously H2O is water. It's also describing the apparatus you're seeing. So that's a good thing that I like to do as well, is to just kind of make sure I understand what's taking place, and most of this is labeled. Here is the start of the experiment. We've got our ethanol, and that ethanol decomposes, producing these two gases, right, C2H4 and water vapor. So you can imagine those two gases, as they're produced, are passing through this tube, and then they pass through this tube and they bubble up into this test tube where they are collected. And it's even got that labeled for me. So right here in this test tube is that C2H4 gas that's being essentially collected as this reaction takes place. So now I'm going to jump down and read this other little introductory paragraph. It says, when the reaction was stopped, 0.0854 liters of gas was collected. So that's an important number that I may have to use. I'm going to underline it, and when it comes to quantitative data like this, I also label, usually I'll label the symbol that you would use to represent that in an equation. Liters, of course, is volume, so that's going to be a V. Sometimes that can help you spot what you might need to do with that number later on. Was collected under a pressure of 0.822 atmospheres, so that's a pressure, and a water temperature of 305 Kelvin. So that, of course, is a T, a temperature. It then goes on to say that at 305 Kelvin, the vapor pressure of water is 35.7 torr. So this is another pressure, specifically the pressure of water. So that would be, equivalent to a partial pressure of water. So I'm going to label that P again, but this time with the subscript H2O, just so that I know this is not just any pressure. This is the pressure of the water vapor at this temperature of 305 Kelvin. So that's all the information I was given. Now let's read the questions and see if we can figure out how to answer them. Letter A says, what gases are present in the collection tube? So that means right here in the collection tube, what is being produced? One of them is super easy. It's literally labeled ethene. So I can fairly obviously say that C2H4 gas is being collected in the tube. There's another gas that's being collected though, and the other gas that's being collected is, it's not really, well, it is a product of the reaction, but we'll see the difference in a second. Anytime you collect a gas over water like this, you have to be aware of the fact that the water is doing something. And what this water is doing is evaporating. You can't stop that process from happening. So that means, despite the fact that most of what's in here is probably C2H4, because the liquid water is evaporating, there's also going to be a small amount of water vapor, water gas, that is also being collected in that tube simply because of the way we're collecting it. We are collecting it over water, so that water is producing its own vapor that is in here as well. So it's a little bit confusing because they didn't label that for you, right? They just labeled it as ethene, but it's not just ethene. There is water vapor in there, along with the ethene gas that is being collected. There's another way you might have known to answer water as one of the gases in that tube. and that's the fact that water vapor is literally one of the products of the reaction. So it's very possible that as the C2H4 and H2O goes through this tube, that some of the water vapor that's produced over here from the ethanol decomposing actually makes it up through those bubbles and ends up being collected as well. So that's letter A. Let's move on to letter B, which says calculate the partial pressure of each gas. So this plays on the fact that in this collection tube, let's shade this in green just to help keep track, that is not just one gas, that is a mixture of gases. And anytime you've got a mixture of gases, that mixture is subject to one of our gas laws called Dalton's law of partial pressures that says the total pressure of the mixture is equal to the partial pressures of whatever gases make up that mixture. We know from question A, we have two gases that make up that mixture, the C2H4 and the water. So I can probably answer this question by playing around with this equation. The question is, do I have any of these pressures? Let's take a look. Some of these things I labeled before, two of them were pressures, right? So the first one says that the gas was collected under a pressure of 0.822 atmospheres. That is the overall total pressure inside that collected gas. So I can plug in 0.822 as the total pressure. We're told that if the water is at 305 Kelvin, the vapor pressure of the water is 35.7 torr. So I do know the partial pressure of the water. The only one I don't know is the partial pressure of the C2H4. You have the extra issue of your partial pressure of water is in this unit torr, and the other pressures here, at least the total one, is in atmospheres, so we're going to want to convert that over, torr into ATM. This conversion is actually provided on your AP chemistry equation sheet, where it'll tell you that 1 atmosphere is equal to 760 torr, and this gives me 0.04697 ATMs as the partial pressure of the water that I can now plug in. So with that plugged in, a simple subtraction tells me that the partial pressure of the C2H4 is 0.775 ATMs. And just to help keep track, let's circle that answer as one of my answers to question B. And then the partial pressure of the water, you could answer in the 35.7 torr, or you could answer in the ATMs. It makes no difference. Let's just circle in the ATMs to keep everything consistent and label that. So that takes care of question B. The last question is question C that says how many moles of each gas are in the test tube. So for this, if we just go back and take a look at some of the values we've got in this, this last little paragraph, things like volume of the gas, temperature of the gas, the pressure. Now I've got the partial pressures of each individual gas. That should jump out at you as a scenario where you might be able to do PV equals nRT, because of course that lowercase n is your value for moles. What you might not have known is that if you use this PV equals nRT equation, and if you only plug in the pressure for just one gas at a time, so for example, let's start with the C2H4. For that P value, I'm going to plug in just the partial pressure of C2H4, that 0.775 ATMs. If I use the pressure of only C2H4, then I will be solving for the moles of only C2H4. The volume of each gas, of course, is the same. That's the 0.0854 liters. Moles is what I'm solving for. I'm going to keep it in ATMs and use the 0.082. I'm not writing all the digits there. R value. The temperature of the gas, you could assume, is the same temperature of the water itself. It's the only temperature we've got, 305 Kelvin. So if you do this math, you'll end up with an N value of 2.65 times 10 to the minus 3 moles of C2H4. You've got to do this all over again, so a totally separate PV equals nRT, except now, for the pressure, I'm going to use the pressure of the water, the 0.04697 ATMs. All the other values are going to be the same, and this time I'll have the moles of just the H2O. And this comes out to 1.6 times 10 to the minus 4 moles of H2O. That completes this question. Thanks a lot for watching.